Hello, everyone, and thanks very much for organizing such a great workshop. So today I'm going to talk about multimodal language and graph learning in catalysis. One of the big challenges that we have in catalysis, obviously, is the humongous search space for optimal catalyst design, and that goes both to bulk crystal structures and then also the adsorbate. We have the surface orientation, which is completely in the combinatorial space is pretty huge. Then we have also the adsorption side that we need to define both the localization and also the molecular orientation. So putting all this together, it becomes a very kind of like exhaustive search or large search space optimal design. So far, during the past last decade, actually, we had GNNs, which are the prevalent type of ML approach for atomic systems, and they are taking advantage of the spatial coordination of the atoms, and we have seen tremendously large amount of efforts on developing models, and starting with the CGCNN and then moving toward DeepNet++ and then GEMNet, which, as you can see, the history from 2021 up to 2023, that we have seen a great type of progress in reducing the amount of error that we are getting with the graph neural networks. However, there are still challenges existing. So one of the challenges is that GNNs cannot, to some extent, accurately predict the periodicity. We have large reliance on the spatial data, which is the configuration, and sometimes we don't have the crystal structure available. And also, the another challenge is how we have the limitations in integration with the knowledge that we have in the literature from different data sources and modalities, and we don't have autonomous agents specifically or specific solvers that we can pull together all the data that we have. So to address those challenges, I'm going to talk about the three efforts that we are doing, and most of this is with my great PhD students, Hoon, which I inherited from Zach's lab. Thanks for leaving CMU and going to Meta and giving Hoon to us. So the first one is language model for property prediction, in which actually we totally migrated from the graph and we use textual description. The second one, we just got accepted in Nature Machine Intelligence, is about multimodality, just pulling together the graph and language. And the last one, which is in prep, is the LLM agent for configuration search, which is really dependent on the previous also talk that we talked about ChatGPT. So the first one, there are different methods to represent atomic structures. So you can go to the coordinates and parse the coordinates. You can use graph, which I talked about. Also, you can use a SMUs, which we have in organic chemistry, in the organic chemistry and the community, and we ourselves were using a lot of the SMUs representation for developing a foundational model such as Morphomer that we did in JAX and Transpolymer for polymers. And then there's another way to explicitly talk about the molecule, right? So say, for example, for chloroform has a molecular structure consisting of a central carbon atom and blah, 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 blah. And then you can write a big description, right? For example, for water, you can write 2,000 books, right? But if you wanted to load the graph, it's only 2 edges and bonds, and then 3 nodes. So to that, in this paper in HCS Catalysis, what we did is that we used ChatGPT in order to parse the textual description of a catalyst system, including the adsorbate and then primary interacting atoms, secondary interacting atoms, also using some of the potentials of robocrystallographer, and other tools. And we combine and pull together all these textual descriptions of the system together. And then you can, as soon as you transfer all this structural information into a text, you can use the pre-trained Roberto or any kind of encoders that are BERT-based and fine-tune them for energy prediction. So that's what we did here. There's, of course, ablation studies that you can do. For example, you can play around with what type of strings you can actually parse in order to get a better results. And you can see the MAE values that, for example, with this string 5, which is the putting primary interacting atoms, site types, bond distances, I mean, we get a better result. The results are on par with the GNNs, but we have challenges. I mean, when Cat-Berta does not perform very well when encountering unseen adsorbates, but for some of these, you know, I mean, like benchmarks that we did specifically here, you can see that with CGCNN and other models, we are not bad. I mean, this is a good, actually, first attempt in using only text for describing the system. Also, you get some benefits. So, and thanks to the transformers, I mean, they have attentions and attention scores, and there's a package called attention visualization package, which you can go ahead and, you know, look at different layers and see what are the attention scores and where it is attending to effectively. And we saw that, for example, there are sometimes, I mean, there are much more interacting atoms from the adsorbate sites, that it is doing attention, attending to the model, and attention concentrates on specific tokens effectively. Also, I mean, like looking at the latent space before fine-tuning and after fine-tuning, you can see this beautiful segregation of the domains for example, different types of elements, so which is asserting effectively the learning that is happening through adsorption. So the second part that I wanted to talk about is multimodal language graph, which effectively is synergistic learning of language and graph together. So, and also we wanted to see how we can infuse the geometrical data into a kind of like text encoder, which is very important. So, as I explained before, we have so far beautiful graph representation models that have been developed in the community, which they are able to distinguish structural nuances, and they have high accuracy by now by the equivariance models and graphs. And most of the graphs right now, they have attention as well, so they are gut-based. And then also we have the text representation, which effectively that I talked about, how you can create a text representation. And then the question is that how we can pre-train. And then there's this beautiful methodology called CLIP, which is the contrastive learning image pre-training, in which you can have two modes of the data. You can take two encoders, effectively encode each of the modality of the data into the latent space. Then into the latent space, I mean, when you have the two embedding, you can multiply them, and you have a cross-correlation matrix, which you can see the cross-correlation matrix here. And since they are coming from the same source, so the cosine similarity on the latent space should be 1. It means that the diagonal matrix effectively should be all 1, and you should wash out off-diagonal actually values via a loss, which usually people use Barlow-Twin loss or other Twin losses. So you backpropagate effectively to both encoders. But there are challenges here. So, I mean, like we have a work in JAX on metal organic frames called Morformer. There, actually, we were able to co-train both encoders, but sometimes it's super challenging. So you need to freeze one of the encoders. Even if you freeze one of the encoders, again, in the other branch, which is Cat-Berta, is infusing the geometrical information. So we use the Equiformer V2, which is the best graph encoder. So you can use any type of graph encoder. And then the Cat-Berta, which is in-house development that we had. And we did, and then you know the Equiformers, I mean, architecture is here. It has got graph attention, and then what we need to do is just using the max pooling layer. So we see a very good effect on the OC20 data sets. So Cat-Berta, you can see that the MAE, for example, for 460K data set is 0.713, and then we reduce it to, and in all the categories that we did, there's a roughly 10%, 7 to 10% enhancement. And I'm very hopeful about the clip pre-training because I think contrastive pre-training is one of the methods that we should do. I mean, we took it also. We have a paper in molecular, which we brought it into organic chemistry for drug discovery. And I think contrastive learning is the best type of pre-training for molecular stuffs. So also we see an interesting shift in the baseline in the attention score. So for the baseline, which is the Roberta pre-train and Cat-Berta, the focus of attention head is much more on the adsorbate. But as soon as we infuse the graph and geometrical information, we saw a kind of like a shift toward configuration space, which is the configuration of the adsorbate on the catalysis surface. And that's what you can see here. So when we sent this paper to the review, they said that, the reviewers said that, okay, so what's the point? To some extent, you need, again, the structures and things like that. So you cannot get it. You really need the structures, and then you, again, to describe things. So in order to answer the reviewers, we fine-tune crystal LLMs, to get to go from text to the CIF file, and then effectively use that as a geometrical information, because in the introduction we wrote that our methods is able to actually only work with text, which is true, because when you get the Cat-Berta encoded, it is already being pre-trained, so you don't need actually graph later on. But anyway, so we find a way to fine-tune crystal LLM, which is a great, I think, paper for generative design of the LLMs, and then we fine-tune it with autoregressive actually generation until terminations, and then we get the adsorbate crystal information as a text, and then it is able to create, a CIF file, and then we parse it. You can see some of the samples of the CIF file that are out there. So with that, actually, we did the LLM derived configuration, which can help predictions. And also we have a prediction inclusion ratio that you can see here, that they're helping the predictions much more. The third part of my talk is about how we can explicitly use LLM agents for configuration search. And that is mostly like involving GPT-4o, and how we can just use them as a kind of like both design of experiment that we heard in the previous talk, and also how we can use that in the catalysis. So we created something called adsorb agent framework, in which we send a query, for example, like derive the most stable adsorption configuration for, and then we parse the adsorbate as a text. And then also we parse also the catalytic surface system, these two ones. And then we created a solution planner and critic. Both of them, they are ChatGPT, GPT-4o. And we benchmarked it with GPT 3.5, 4, none of them as good as 4o. But the cost is more because we are pulling the API many times. What Solution Planner does, the questions that we are asking the Solution Planner via meta prompt and then segregated prompts after that is that, are the adsorption sites providing the adsorbate with sufficient metal atoms to bond with? Is the coordination number appropriate for the adsorbate, considering the bonding preference? So we ask multiple questions. Prompting here is super important. Then we created a critic, which there's another LLM which is discussing and debating if it is right or not. So it is actually kind of like adversarial learning on the LLM. And then that gives us the site type, binding surface atoms, binding adsorbate atoms, and orientation. Also, it gives us to some extent orientation. Then we created a binding indexer, which is another actually LLM, which it designates the index of binding atoms in the adsorbate to place the adsorbate according to the specified binding atoms and orientation. And then with that, we have a script that we put together and we generate the configuration. After that, we have great relaxation and anomaly filters based on the GNNs. You can call them via the API, and you can effectively go to the most stable configuration. So the results are actually very good. I didn't expect this. So you can see the random search and heuristics. Actually, it takes like 59 and 58 types of steps, where for LLM assisted, the random is 7 and heuristics for the rhodium tellurium surface is like 8, which we significantly reduce the search effectively via LLM assistance. Another example case study is the nitrogen reduction reaction, NRR, which is a super cool, and highly applicable type of reaction for producing ammonia. But as you know, I mean, it has a major challenge is that there's a kind of competing HER, which can interfere with the process based on the literature data from Open Catalyst project, I mean, on the NRR, and you can see on the graph on the literature results for that. So actually, we applied the LLM assist or absorb agent, and there is also here of very interesting. Even we found actually a much more lower energy, a stable energy. So you can see with the OCP demo, Open Catalyst project demo, for both random and heuristics, you need 98 steps to get to the minimum energy of 0.755. With our absorb agent, it only requires 22 steps. We got to the energy of 0.733. For the molybdenum palladium surface, OCP demo, random and heuristic is 59, and actually absorb agent found it in 4 steps. So it was very quick, and it was a much lower energy. So I'm super hopeful that it significantly reduces the amount of calls for energy prediction for minimum energy prediction of a stable configuration. So this is the visualization of Relax. Relax actually at slabs, as you can see, for both surfaces, and the amount of energy, minimum energy that we got via using LLM assisted actually search. Also, this is another lower relaxed energy with fewer configurations. I mean, that you can see how much the original OCP demo, the orange bars show how much effort exhaustively you need to use, as opposed to absorb agent, which is using the LLM. Okay, and I have a short outlook about LLMs and all generative models and actually foundational models that we are doing. And I think, I mean, this is the time to have a kind of like comprehensive design platforms. We are seeing papers like AI scientists and all these efforts. So I think we need to create and we are pushing that to create a catalyst agent which actually talks to different sources like literature and web, talks to different kind of repos like Crystal LLM. Gen AI models, PyMath also has physics-based / data sets and API, and then it can go and accelerate actually the discovery of catalysts. Okay, I think that's my last slide. Thanks again to Hoon. These are all his work and all other my PhD students and the funding agencies. And this is my lab. Thank you very much.
Questions?
Yeah, sure.
I mean, a very nice talk. So I have a quick question. I noticed that in your configurational search section, you focus on mostly stabs or crystalline surfaces. I wonder if you have tried or plan to try for these older surfaces, or like say clusters where you don't have a very well-defined sites or local binding.
No. But we are we didn't. This is very preliminary results we developed in the last 2 months. Yeah, and it's mostly on the OCP, demos and the data sets. But I think moving forward, we should do that and to make it much more generalized. Yes.
Yeah. So very cool work, but I see a lot of people are using LLM right now. So, but because LLM did do auto regression, so basically they're sampling from all these token dictionaries. How do you say this? So basically you ask with GPT with a template of questions,
Yes.
and you click that regenerate. So it might give you a similar answer, but not every word or every character, every token is the same. How you like process this type of uncertainty?
Yeah, you're right. I mean, so this is a piece of code. You can see that, I mean, that we are doing. That's actually, it's not a closed feedback loop. You're right. I mean, so everything, I mean, depends on the initial prompt that you design, and that should be so good. That's why we put the critic, to go back and forth. So the critic module is actually another LLM which looks out to the response of the first LLM, and this is the pseudo code. Actually, this is the actual code, I think. So this is just, I mean, putting some chunks of predefined prompts and then adding that to, for example, I don't know, knowledge or absorption site type. So, and that is taken from, for example, the dictionary that you are doing. And then, I mean, there are a lot of, I think, LLM agents that, as you mentioned, are working now. I mean, you can see this paper in alloy design. I mean, these are really like, I think it's popular. And then we ourselves also giving something called printer 3D printer control, which we are calling like 100 times the LLM agent. So I think, I mean, moving forward is the time for LLM agents.
All right, I think it's time for our coffee break.